ICAO document 9859, advising on aviation safety management, gives an account of how accident prevention has developed since the Second World War. One key point made in the accounts relates to how behavior is adjusted whenever undesired events occur. The model presented focuses on how safety performance of an operation drifts from a design baseline. In earlier times, the safety performance could drift unimpeded until an accident occurred. The negative exposure accompanied by an accident would then trigger a change in behavior, forcing the safety performance to improve, at least for a while. As air travel increased throughout the golden era of aviation, it became unacceptable that safety performance was accident-driven, and mandatory incident reporting and later yet voluntary incident reporting was introduced for events that in themselves did not qualify as accidents, but could easily have led to one. Among other things, this was a driver to improve safety performance. The rationale behind ICAO document 9859 is to advance the safety performance driver further up the drift stream. Implementing ICAO or EU SMS into an existing training organization with years of operational experience may be hard. When examining the requirements of the EU aircrew regulation, it may not seem apparent how to fit the provisions into an existing operation. One key to understanding how to implement SMS may be to view the requirements from the perspective of performance management. Imagine a person who is unhappy. The person is the system. The unhappiness is the system performance. If the person wishes to be happy, the system performance is low. This person carries out a study by consulting a therapist and discovers that his or her unhappiness is founded in overweight. In order to increase the system performance, the person sets an objective to lose 60 pounds. Since the objective will not realize itself, the person determines a policy that will support the objective to lose weight by eating less food and exercise more. The person wishes to monitor progress and decides to measure the daily calorie intake and the daily calorie consumption. Additionally, the person chooses to record his or her weight one time each week. Let's consider this as the initial system state and note the following. There is an objective defined that is concrete and measurable. There is a policy that outlines how the objective will be obtained. There are indicators that will provide early warning, and system performance can be monitored in real time. Note that the indicators relate to the objective. Performance indicators are available in two types. Leading indicators revealing trends on future system performance. Lagging indicators recording actual system performance. When placed in the production process stream, the leading indicator should be placed upstream and the lagging indicator downstream to make use of the principle that the leading indicators can supply early warning on degrading system performance. In the unhappy person example, you'll see that the calorie balance is a leading indicator, since it may indicate that the expected weight loss will not occur if the intake becomes excessive. The recording of body weight then is the lagging performance indicator, since it will only occur after the policy has had runtime. Finally, you'll see that the system performance can be assessed in relation to the objective or in relation to the actual system performance. In this case, the person may lose weight according to the objective as predicted in the initial study, but the actual goal was to obtain happiness. So there is a formal performance as well as an actual performance that needs to be considered. Because of this, the system needs to be reviewed at regular intervals to prevent the objective to be misleading. If the person is not happy, though weight is lost, the objective needs to be reconsidered. You may recognize this principle from William Edward Deming's plan, do, check, act wheel, which is often referred to in quality management. But rather than to continue monitoring the same system elements, performance-based SMS is concerned with the change of system environment. If we stay with the example of the overweight, unhappy person, he may forget to measure the calorie balance or the weekly weight recording. Perhaps this will have no impact on the person's eating habits and may not harm the objective, but this forgetfulness may lead to the loss of control of the process, and many people dieting will agree that this most certainly leads to old habits kicking in, and no weight loss or maybe weight gain will follow. The person in the example chooses to have a friend remind him regularly. This action in itself will not make the person lose weight, but it will perhaps prevent the threat to the objective from appearing. These few actions are the basis of safety management and comprises of identifying hazards and manage associated risks. So a few new terms are now introduced. Hazards meaning a potential threat to the objective, and risk meaning the assessment of the severity and probability of a hazard. Specifically in ICAO SMS reference frame, aviation hazards are defined as a situation that hold the potential to cause injury, damage, or degraded system performance. Note that hazard could just as easily and perhaps more correctly be referred to as threats. This is probably avoided to prevent confusion with the threat and error management terminology used operationally. Here's a hazard, here's another one, and another one. You see that a hazard in itself is not a relevant element. Only when the assessment of probability and severity have been accomplished will the element, now called risk, have relevance to the performance management. The earlier suggested asteroid impacting the Earth would probably be a catastrophic event, and though it may destroy most life on the planet, it has only happened a few times throughout Earth history, and the probability may be considered so rare that the risk may be considered very low. On the other hand, a mosquito bite may seem to have an insignificant severity, but it may be rather frequent, and considering tropical diseases, it holds a risk that is much higher than the asteroid impact. It is quite open how to assess risk. Some organizations may be more willing to accept a higher degree of risk than others, and every organization will have to determine what it considers an acceptable level of performance, subsequently what risks are acceptable to it. The essential part is that hazards are identified that relates to the objective and that the associated risks are determined. We saw in the example of the unhappy person that he introduces an action to avoid the performance degradation by having someone remind him to measure system performance indicators. The unhappy person introduces hazard identification by identifying a potential threat which he considers to be a significant risk. We can't tell from the story how the risk was assessed, but we can see that the risk was assessed and that its impact was not acceptable. How did we know, you say? Well, a mitigating factor was introduced to bring the probability down to a lower level. As you recall, risks are composed of both probability and severity. So an alternate method for the unhappy person could have been to reduce each meal size. In that way, the severity from forgetting to measure calorie intake would be smaller and thus the risk would be reduced. But perhaps this is not a plausible reaction from a dieting person. The act of reacting to risks in this manner is formally called risk management. ICAO defines risk management as the process of assessing identified hazards for probability and severity with regards to the objective, determining acceptability of the risk, and if required, putting in place mitigations to reduce the risk, and verify that the mitigating action is in fact having the intended effect. Again, you see the repetitive elements familiar to some from the principles of quality management. Allow me one final narrative of the unhappy person. The formerly unhappy, but now slimmer and happier person has a new job. This new job takes up a lot of time, and the person no longer has time to prepare meals at home. In order for him to have regular food for dinner, he gets his dinner from a fast food restaurant, serving only fatty foods, and it is no longer possible to balance the calorie intake to achieve the objective, and the leading performance indicator now shows that performance will degrade. Sure enough, as we all know, eating deep-fried foods does not go unpunished, and within days the lagging indicator shows that the weight is increasing, or perhaps not decreasing towards the desired 60 pounds loss. As seen earlier, you notice that the objective is jeopardized, though other factors may support that the actual system performance is not degraded if the person is still happy. Perhaps the new job is more important to happiness than the weight loss. The moral of that part of the story is that whenever change is introduced to the operating environment, new hazards will appear. If the organization have selected good leading performance indicators, the impact of the change is likely to be detected early on, enabling proactive management. If the organization have selected poor leading performance indicators, the impact of the change is likely not to be identified until triggering the lagging performance indicator, enabling only reactive management. So before venturing into the subject of implementation in flight training, let's recap. Performance-based management means obtaining real-time information on performance by detecting one or more objectives, selecting a policy by which the objective is to be achieved, identifying hazards, selecting leading performance indicators for risks, and selecting lagging performance indicators for risks, which will give you the opportunity to detect performance degradation before it impacts the operation. If you want to implement performance-based safety management into a flight training operation, you must determine what you're required to manage. You need to identify the hazards in your operation. I propose to focus on two areas: hazards that are present during the training and hazards that are the consequence of the flight training. Some training departments may take offense of the second proposed hazards, but keep in mind that there may be a significant difference between training and learning. Training is no guarantee of learning, and a large part of all accidents involves a formally qualified flight crew. The hazards encountered during training are all the reasons that the authorities will not allow persons to come in from the streets and fly airplanes, and they are also all the reasons that you yourself will not lend your own plane to anybody that haven't had flight training. There are probably different hazards on training flights carrying a flight instructor and training flights for student pilots flying solo, the flight instructor being a mitigating factor allowing training in more hostile environments. During synthetic flight training, there will probably not be many operational hazards other than falling off the simulator or using the escape rope ladder. In 2001, an Airbus 300 crashed into a residential area. The National Transportation Safety Board concluded that one probable cause was the separation of the vertical stabilizer as a result of the loads created by the pilot's excessive rudder inputs following the reaction to a wake turbulence encounter. The NTSB found that the pilot did just as described in the simulator training program. So to have any value relating to safety management, synthetic flight training operations should focus more on identifying hazards related to inadequate learning than to operational hazards. Introducing SMS should not be done as to create a parallel management branch inside the training organization. To have any effect, it should be adapted into the existing structure. and granted, it needs to have a certain amount of formal management from somebody. You should also consider your choice of hazards to measure and avoid to let availability of data lead your hazard identification process, ending in measuring hazards that are not really relevant but chosen out of lack of insight. Remember that you have a regulatory commitment to improve the system performance. This should prevent you from selecting irrelevant hazards that are not really hazards. Choosing this type of non-hazard will become evident from the fact that your performance indicators will show that the hazards in reality are not a problem. This will force you to choose new hazards to focus on, making the process a waste of resource. Commercial air transport operators have for some time had flight data monitoring programs that allowed them to identify and act upon undesired trends in the flight operations from recordings of aircraft parameters. Such a program points to the core of hazard identification since it provides objective evidence of actual performance. Luckily, though, this requirement is not yet mandatory for smaller aircrafts often used in flight training, but it shows us what is meant to be achieved, actual results from the operation. I propose that you group your hazards into flight phases that corresponds to your training program. This will allow that you use the flight lesson documentation as a vessel of data collecting similar to flight data monitoring. You can do this chronologically or thematically. Let's try some. I consider students making landing with a hard nose wheel touchdown to be a problem. Too many O-rings in the oleo assembly fail prematurely. This is a valid hazard since it is reducing the aircraft system performance and it has a high potential to be harmful and cause damage. I already determined the outcome to be unacceptable, too many failures, so the risk is now managed. The lagging indicator could either be O-ring failures or nose wheel touchdown. The leading indicator, I would say, could be failure to recognize correct flare initiation height or perhaps incorrect touchdown attitude. But it might also be incorrect airspeed in the final approach or a number of other things. My experience as a flight instructor tells me that incorrect touchdown attitude is the better indicator. I select a band of attitudes inside which instructors may allow students to operate in landing situations and ask them to take over flight controls if this attitude window is exceeded. I will introduce touchdown attitude as part of the grading system on the lesson plans and can now start to record data. Here are some other examples of situations where one could have concerns with regards to poorly trained persons. First, aircraft training. For the synthetic training, it's evidently not hazardous to perform any of these items in the simulator. They are, however, situations from a transport category aircraft in which the pilots are not telling jokes, but are quite focused on avoiding the undesired outcome. This focus is obtained from training, and trainers that are engaged in type-specific simulator training should identify these situations and measure their training effectiveness as part of the safety performance management. When recording safety performance along with student performance, it's important to note that these two types of performance serve different purposes and the grading should not be combined. Student performance measures degrees of excellence and perhaps also drives student motivations or other factors. A safety performance indicator looks for system failures, and it's not given that poor student performance will provide useful information in the SMS context. Instead, I propose this scale that concerns degrees of substandard functionality of the program. Note that the grading scale puts emphasis on the degrees of poor system performance to more easily identify a system improvement. Also note that if the risk continuously records as not being a problem, it's no longer relevant to measure it, but other hazards should be identified and managed instead. Remember that the message is not that the organization that have provided flight training until now are not safe or poorly managed. Nor is the message that what we do is dangerous. Flight training has been performed safely in decades. However, as you noted in the beginning, SMS is meant to be a method to intercept those safety threats early on and to move the task of safety management from the regulator to the front line of the operations and let organizations carry out part of the oversight themselves.